Okay, today we are going to talk about graph problems, but we are going to talk about graph problems in the streaming model. And you may be wondering how this can be done, so let's dive into it to see how it works. But before we get started, so let us motivate the context a little bit. In regular graph problems that you might have studied in a typical algorithms course, you expect the entire graph to be available to you, but that is not always possible when the graph is very, very large. So this is, after all, a course in algorithms for big data. So we want to consider a context where the graph is so large that it won't fit into your one computer, and as a result, it's not accessible to you. The entire graph is not accessible to you, but rather it's only accessible one edge at a time. And this could be for a variety of reasons. One common reason is that the graph is actually not stored in one computer, but it's stored across multiple computers, multiple servers in a large data center. And so the only way you can explore the graph is to actually have a bot, which is basically a little program that hops from one server to another server, following the edges. So this, as far as from the bot's perspective, it only sees one edge at a time. And so this is one perspective of how we might be able to, how we might encounter a situation where we only see one edge at a time. And the other possibility is that the graph is so large that you cannot really load it up into main memory in one shot, but you just do a single for loop over the entire set of edges, and you get the edges in some order, and you perform your operations on that for loop. So you only get one pass through the entire set of edges. So these are just a few motivating contexts where such streaming algorithms might be useful. So let's study this a bit formally. Let's begin with a clear statement of what the model is, the computational model. Our real input is a graph G with vertex set V and edge set E. And we use n to denote the number of nodes and m to denote the number of edges. And the edges might be weighted or unweighted. For most of this lecture, we're going to assume that the graph is unweighted, but when weights are relevant, we will mention them. Now, this graph is not directly accessible to us, but rather the access to the graph is through a stream of edges, one at a time. So the access to the graph is only through a stream of edges. Okay. And we see one edge at a time, and after we've seen that edge, we have to let go of that edge, and the next edge shows up. We have to process that edge, and then we let go of that edge, and then the subsequent edge shows up, and so on. And as we run through the edges, we're allowed some space, but we're limited to some space that's of the order of n times a polynomial in log of n. So of course n is the number of vertices, and keep in mind that the actual graph, the size of the graph is actually could be dominated by m. So that can be as high as O of n squared. So now we're not allowed to store, if we are allowed a space of O of n squared, we can simply store all the edges and then let all the edges go through, store all of them, and then process all the edges in one shot. And we will basically be able to store the entire graph. But that's not allowed. We're only allowed to store n over polylog of n number of bits, which means that we have to be a little bit careful. And this is a slight relaxation of the usual streaming model where the actual memory that we can store is actually much smaller, say typically only log n or maybe log squared n or something like that. But with such small memory, graph problems tend to become oftentimes impossible to solve, and so we give ourselves a little bit more memory, and this as a result this model is called the semi-streaming model. So now we can think of variance. In this variant we are getting one edge at a time, so we can think of it as we're starting with an understanding of the graph being just the empty graph, and then as an edge comes we can think of it as getting more and more information about the edges. But it's also possible, some variations that you can think of where edges are added but they could also be deleted, and that complicates things, but we will not be considering them in our lecture today, but you can easily imagine that these are possibilities. Again, other varieties include changes in the edge weights and so on and so forth that can be streamed into the system, but we will ignore all of those variations for now. We're going to stick with this variation where we receive one edge at a time. So we're going to stick to the basic model, and a lot of times for simplicity we're going to assume that the vertex set is basically labeled 1 to n. Okay. So this will mean that we have n vertices, and we can assume that they have an integral label from 1 to n. Okay. So here's an example, just a quick example of a graph with 4 nodes, and so an example input stream will be first that we get the edge 1, 2. So we get this edge, and then we get the edge 2, 3, which means we get this edge, and then 1, 3, then 3, 4. But there is no reason why we should get it in this particular order. We could have also gotten it in a completely different order. So for example, the first edge could have been 3, 4. Then the second edge could have been 1, 2. Then the third edge could have been 1, 3, and then 2, 3 at the very end. So we're not making any assumption about the order in which we're going to receive the edges, but we're going to receive the edges one after another, and with that we have to answer some questions. So let's without further ado, let's start with a very basic question of connectivity. So we have this graph, and we're getting an edge, one edge at a time, and we want to know whether the graph is connected or not. And so how do we do that? Let's say that the first edge we get is say 3, 4. Okay, we include that, and let's say we keep the next edge that we get is 1, 2. Okay, at the moment this is all the information we have, and we keep collecting such edges. So let's say the next edge that we get is 3, 2. So we build our graph, and then the fourth edge that we get is 1, 4. Now the question is, should we what do we do with the edge 1, 4? So just to remind ourselves, so we got the edge 3, 4 first, then we got the edge 1, 2, then we got the edge 3, 2, and now we've gotten the edge 1, 4. But notice that the whole point of this current problem is to check for connectivity. And we already, given the information that we have, we already know that 1 and 4 are connected. And with that being the case, there's no real virtue in including this edge 1 to 4 in our data structure. So we simply can avoid this edge. And then let's say we get an edge say 4, 5. We add that. 6 comma 7, and let's say that the stream stops at this point, then we know that the graph is actually not connected. But on the other hand, if following this we got an edge 2 comma 6, then we know that the graph is connected. So as the algorithm progresses, we are maintaining a forest, and at termination time, if it is a forest but not a tree, then we know that the graph is not connected. But if it is a tree at termination time, we know that the graph is indeed connected. So this is a simple example of a way of a streaming algorithm that reports to us whether the graph is connected or not. Let me add one little point about the model. We know we have n vertices. We're going to assume in general that this n is known to us in advance. This is not a very important assumption. Sometimes we can get rid of it, but for simplicity, for our purposes, we're going to assume that n is always known. So in this case, if n is already known, always known to us, the moment we create a tree on n vertices, even if, we can terminate at that point itself. Okay. So now let's ask a slightly more advanced question, and for that let's define a notion called spanners. What is a spanner? Well, let's say you're given a graph G. What you want is a smaller subgraph that sort of mimics the connectivity properties or the distance properties of the original graph. So the original graph could be a much more complicated graph, and what we want is a sparser graph H, and typically a subgraph H. And that subgraph H, the distances in the subgraph H should be an approximation of the distances in the original graph. And this is very useful because if the original graph is too complicated, and but if we can construct a spanner that has fewer number of edges, it will occupy less space. So this is one way of taking a large data set and approximating it by a smaller data set that gives you reasonably good approximate answers to whatever distance queries that you might have. Let's be a little bit more formal now. Given a graph G, we say that a subgraph H is an alpha spanner. Here alpha is a parameter, is the approximation parameter. We say that H is an alpha spanner for the graph G if for every pair of vertices. So now you have a graph. Now you take any, this is let's say G, any pair of vertices U and V, there is a distance between U and V in that graph G. So that is your DG U comma V. Okay. Now multiply that by alpha. So let's give ourselves some examples. So let's say DG of U comma V is 100, and let's say alpha is 1.5. So let's assume alpha equal to 1.5 as an example. Now, so this is 100 and this is going to be 150. So this gives us a range to work with, and from G we want to construct a subgraph which is H, and we say that H was a subgraph if the distance between if H is an alpha spanner, if the distance between U and V in H is sandwiched between the original distance between U and V and alpha times the original distance between U and V. And this means that this inequality is going to be easy to attain, but what might happen is what needs to be ensured is that by making the subgraph smaller, we have to ensure that this inequality is also respected. In other words, when you reduce the number of edges in the graph H, you don't want to blow up the distance beyond alpha times dg of u comma v, and this must be true, remember, for all pairs of vertices u and v. Okay. So this is the definition of a spanner. And why would a spanner be useful? Only if H has a far fewer number of edges than G. If that's the case, then H is will occupy a lot less space and will be a very good approximation of graph G. So let's look at an algorithm to construct a spanner, and we're going to look at it from the streaming model's point of view. And it's actually very simple. You start with the spanner being the empty set. This remember, this is our spanner H, and we stream through the edges. So for each edge UV. Now here's the condition that we need to check. Now we're going to be maintaining a graph H. Initially this H is going to be empty, and when we get an edge UV, we ask ourselves what is the distance between, we are maintaining a current H, and we're asking what is the distance between U and V in this graph H that we are maintaining. Okay. And if that edge, and just to remind ourselves, we are thinking of this is an unweighted graph. Now if the actual distance between U and V, this is that's the, let's say, the shortest path between U and V in H, if that distance is greater than alpha, then that means by including this edge, you are going to be ensuring that you're not overshooting that alpha approximation, right? Because now this means that you have to add this edge UV if this condition were to hold, and which is exactly what we're doing. Now if this condition were to hold and we did not add UV, then we are immediately violating the alpha spanner condition. Okay, so that's why we must add UV. And as it turns out from this, what we realize here is that just by ensuring that UV is added in this, when this condition is encountered, then the algorithm overall is correct. So for each edge UV, you just check if the distance in the spanner that we are maintaining so far between the vertices U and V is greater than alpha. If it is greater than alpha, then we must include the edge UV in the spanner. Otherwise, we can we don't have to execute this inclusion line over here. Okay, and at the end we just return H. Now, why is this algorithm correct? So this algorithm is correct because now if you have a path, let's this spanner condition should hold for any pair of vertices, right? So now let's say you have a path from A to B to C to D. Okay. Now in the spanner you may not have added all of these edges. So let's say you have A and B, I mean you have A, B, but you did not include BC. Okay, but why would we not have included BC? Only because there was some other path from B to C that was of distance at most alpha. Okay, and as a result, the blow up, you can go from A to D by just taking these detours, and that will not blow up the distance by more than a factor alpha. So that's the reason why this algorithm will indeed be an alpha spanner. And of course, now the interesting part will be to ensure that the size of the spanner is within reasonable limits. We'll skip that for our purposes now, but the idea of how to construct a spanner is very important, and I hope that part is clear to you. Okay. Now let's look at a weighted graph, so now we're looking at a weighted graph, and we want to compute, let's say, the minimum spanning tree. How do we do that? Well, this again is a very simple algorithm. We of course start with the empty minimum spanning tree, and we look at one edge at a time, and whenever we encounter an edge uv, we ask if we add the edge to the edge uv to h, and ask if that created a cycle. Okay, if that created a cycle, then we need to be a bit careful now. So whenever a cycle is created and we want to maintain a minimum spanning tree, what we should do is in that cycle we can safely remove the largest weight edge. So let's say we created we have currently a graph that looks like we are maintaining the invariant we'll be maintaining is at the start of each for loop the algorithm will be h will have a forest, will represent a forest, and the forest will actually be weighted. Let's say this is 2, 3, 1, 5, 2, 1, 10, 2, 5. Okay, and let's say these are the weights. And now let's say we add this edge over here, and that edge, this is, let's say, u and this is v, and so we've received the edge uv and we've added the edge uv, and it happens to have a weight of 7. Okay, now what do? We have to we have found a cycle, in which case now in this cycle we have to remove the largest weight edge, and that's going to be let's say this edge is, this vertex is w, that will be the edge uw, and that edge uw must be removed from h. And by repeating this procedure for every edge uv, we'll be maintaining a spanning forest, and if at the end the graph is connected, that h will actually be representing this minimum spanning tree.